Alright, so here we are with the second half of the Chapter 1 and 2 test review. Super. So all the ones I'm skipping here are what I did in the previous video, so you'll want to check that out. So here we are in part 2, starting on page 165, and we're going to find the domain and the range of the function. It doesn't necessarily say how to, so it's probably easiest if we just graph. The way that they have it here, you can definitely see that it's a squared function or a parabola. And then that parabola actually has it shifting minus 2 inside here, means that it's going to go right 2. And then this plus 5 here means that it's going to go up 5 from that 0, 0 origin where it would have started. So in that case, let's see. I guess I don't really need to graph it, but I will for fun. So right 2 and up 5 leaves us here, and then it kind of goes like that. Up 1, over, there we go. So that's where it is, and so if I want to find the domain is going to be all real numbers, as it is for any quadratic, and then the range is going to be stopping at 5, looks like that's the lowest number it will be, and then going up to infinity. So we're talking about all the y's between that. There we go. Alright, so the next piece here, we are finding the range of the function and domain. So probably best if we graph it. What actually seems like it would happen is we could cancel an x from each of these parts. However, what that does is that it makes it so that you don't actually have the hole that would be in there because of that canceling. So it could also be equal to 1 over x minus 2. But again, that gets rid of the 0 where there would actually be a hole. So if we take the time to graph it on our grapher / graphing calculator, minus 2x. I am not in a standard window. There we go. We're going to end up with a vertical asymptote at 2 because of that 2 that would make a 0 in the bottom, but also in the previous one a 0 would have been plugged in to make a 0 as well. And so I believe that's why if we plug in 0, yeah, we get an error. So what's going to happen is there's going to be a graph that goes like this, but then at 0 we're actually going to have an open space. So interesting, sure. And then over here, it's going to go up like that. Alright, so let's go ahead and talk about the domain. This is not a parabola, so your domain is going from, it might be easier if we just say all real numbers, and then say that x cannot be the two things that don't work, so 0 and 2, because every other number will work. And then the range is going to be all real numbers except 0. And then I guess whatever the other value would have been at 0 over here. That's interesting. Let's see table. So I'm going to regraph this. I'm going to graph this equation and plug in an x of 0 and find out where it would have been for this coordinate here. So it's at 0 something. Let's see. Nope. 1 over x minus 2. And so if we go to the table, it should have been at negative 0.5. So that y value is not okay either. So all real numbers, x cannot be negative 0.5. I got that by graphing this piece once it's simplified. And then, what's the other one? It was 0 because of the horizontal asymptote. There we go. Alright, then our next question, We need to graph the function and state the intervals on which the function is increasing. Super. So of course you can graph this by hand if you want, by plugging in some numbers, but no thanks. The idea from this graph is that it would have been kind of going through this 0, 0, but we are going to do what this says, which is move right 1 instead of at 0, and then we're going to go up 2 from that 0, 0. So our official starting point is actually right here, and then it goes up 1 over 1 from there. There, and choop, 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 choop. Tried to make that as straight as possible, and it's very wobbly. So either way, we need to talk about the intervals on which the function is increasing, and so that's just this part over here. So our increasing interval is going to be from the number 1 for x, and then all the way to positive infinity. Super. Done. Alright, then in number 30, we're going to graph the function and tell whether the function is bounded above, bounded below, or bounded. So if you remember back to analyzing our function, this is kind of each part of our lesson was building up to being able to analyze. So this is the part where we talk about if it's bounded or not. So we'll graph 6x. And remember that when you graph this, especially on the graphing calculator, you're going to want to do it so that you have parentheses around the denominator. Otherwise, it might not work as well as you think. Ooh, that is interesting. Okay. So what's going to happen is we have some horizontal asymptote here, and then it kind of does this thing, and then it goes back down to a horizontal asymptote at 0. So we need to tell whether this is bounded above, bounded below, or bounded, and I'm going to say bounded because it is not going to end up going any higher than that highest maximum and that lowest minimum. So you don't have to actually say where it's bounded, so I don't care, but it is bounded, meaning above and below. Alright, and then the next one, since it's got this exponential in here, it's probably just going to be bounded below, although it is a negative, so maybe it's above. Either way, we go to the equation setting of y equals and graph e to the x. E is by the division sign if you use second, and then we're going to bring that to the x power. Ooh, it is bounded above. Alright, so looks like it's at 1, 2, 3, 4, 5-ish. Oop, and then it goes down exponentially, of course. So that means that it is bounded above. Whoops. And again, it doesn't matter what that number is at this point. All they wanted you to know is it bounded above, below, or bounded? Alright, moving on to number 53, we're going to find an expression for f of g of x, fog of x, and give its domain. Ooh, alright. So that means that I'm going to take the f equation and put the g inside of it. So it's going to be f of g of x. That's what the fog indicates. So that means that I'm going to write the red equation, which is just a big old square root of x, erase the x parts, which there's only one of them anyway, and then put in the g equation. Alright, then some of you might think that you can square root this and get an x and square root this and get a 2. However, that is not actually how things with subtraction work inside of square roots. So, we cannot simplify as much as that, but we can factor. It's not really going to do much either. So, we could potentially write this as the square root of x minus 2 and x plus 2. But that doesn't really simplify it, actually kind of makes it look worse. So, we are going to graph it in our grapher. X squared minus 4. And that is very interesting. So what it looks like is an equation that comes down here and then goes back up here. and that's at -2 and 2, because of course those are the numbers that are in here. And then there's actually nothing in between. So if we're going to find its domain is all of the x's between -infinity and infinity, but it's going to stop at -2, and then also stop at 2, or begin again at 2. That looks like another 2. It's not. It's a less than sign. Alright. And then the last one here, g of f of x. So now they just want you to do the opposite of what we did. And so we're going to do g outside and f of x inside. So that means I'll write the outside function, which is x squared minus 4. And then we'll take away the x and write the f function, which is square root of x. And so this is the moment where we can actually cancel the square and the square root. So we'll have x minus 4 as our equation. And since this is a linear equation, that means that our domain is all real numbers. So a line is not going to do anything fancy. Or unexpected. Alright, so in the next one's number 20, describe how to transform the graph into the graph of the given function. So we're going to look for those a's and b's and h's and k's that are extended onto this parent function of x squared. So if we take a look at this one, a 1 and a 1/4 are like the new pieces of this graph, and so the 1/4 is actually going to vertically shrink, and then the -1 is going to move the equation down 1 from the origin at 0, 0. So basically, instead of being your traditional, it is going to shrink that, so kind of compress it there. And then we're going to go down 1, so it's going to shift down instead of at 0, 0. So here it is, and officially I could graph it to know what's happening, but I don't know if it even said graph. Sketch a graph. Perfect. I like that. Alright. Then the next one, we have a -3 that's doing something and a 2. So the -3 is going to, well, the negative part of -3 is going to flip on the x-axis. The 3 part of the -3 is going to stretch it vertically. So instead of getting wider like the last one did, it'll get skinnier. And then the +2 is going to move the equation up 2 units. So up 2 units at 2, flipping on the x-axis, and then also stretching vertically, so skinnier. There you go. Wonderful. Alright, next question. We're going to describe the strength and direction of the linear correlation. So this is just what is our trend looking like, and it's definitely trending down here, and so we're going to say that this is a negative correlation. And we're going to talk about its strength, and we're going to say it's a strong correlation. Basically, the only time it's weak is if it's very sparse and sporadic and doesn't have necessarily a trend, like this one clearly does. Correlation, yeah. Alright. The next one, we're going to match this polynomial, number 29, with its graph and approximate all of the real zeros. Interesting. Okay. So, let's see. I look at this, and I know that that means that it is a y-intercept of 55. And so if we look at all of these, y-intercept is negative here, and positive and positive. However, this one has our y is going from -10 to 50, and so if this is 50, 55 is not even on the graph, so it can't be the y-intercept, so it's not that one. And so it must be part A as our answer. Along with that, we also want to identify what the zeros might be, so it looks like one of them is kind of here on that tick mark, and since it goes -4 to 4, that's probably 1 then. So our 0 is going to be 1, 0. And then the next 0 is over here, kind of between -1, -2, -3, -4. It's between -2 and -3, so we'll go with -2.50. Sweet. Alright. Next one is number 5 on page 269. We're going to find the vertex in the axis of the graph, meaning the axis of symmetry, and support our answer graphically. Super. Okay. So as we look at this, it is a parabola, but what's happening is we're going to end up having a negative, which is going to flip on the x-axis, so it's going to go down like that instead. And then we have a 2, and that 2 out front is going to stretch the equation vertically. So it's going to look skinnier. The +3 that's there means that we're moving left 3, and then the +5 means that we're going up 5. That's supposed to be a +5. So, let's see. The vertex of this graph is, because it's in vertex form, right here. So our vertex is at -3, 5. And then the axis of symmetry is always at x equals the x value of the vertex. So we'll support it graphically by flipping on the x-axis. Okay, left 3, up 5. Let's see. So we're going here, and it's going down, and it's skinny. So here's our vertex of -3, 5, and here's our axis of symmetry at x equals -3. Woohoo! Alright, let's see. This next one is saying write a summary statement, but really we just need to divide and get the result. So it's just their fancy way of saying show that once you divided it, it got this answer. Does not say how to divide, and since this is x minus 3, we can go ahead and do synthetic division with a +3 here, because remember that this thing over here is always the 0, and this is the factor. So to get to 0, you do the opposite. Then we have to double check that all of the powers are here, so 3, 2, 1, 0, so we don't have to add any extra zeros in. And so to solve, we bring down our 2, 2 times 3 is 6, add those values, -1, -3, add those values, +1, 3, add those values, 2. So our remainder is -2, which means it doesn't divide, but that's okay. So officially what they're saying is if we take f of x and divide it by d of x, this is like our summary statement, we're going to get 2x to the power of 2 minus 1x from this guy here, plus 1, and then our fraction of -2 over x minus 3. You could also make this positive a negative because of that -2. Doesn't matter. Just I wanted to keep it with it because it seems more like a unit to me. The next one does have to be long division because it's got a squared in it. So whoopee, 4, 3, 2, 1, 0. So we do have all of the pieces in what divides into it. Alright. So there's two ways of dividing this, and okay, I'll do it the right way. So there's x squared plus 0x plus 4. And then inside we have 2x to the 4th minus 3x cubed plus 9x squared, very exciting, minus 14x plus 7. Alright, so first thing we do is look to the 2x to the fourth and the x squared and say what's missing from both of those in order to get 2x to the fourth. So clearly we're missing a 2 here and an x squared in order to get up to x to the fourth. So 2x squared is going to go here, and then we multiply into here, here, and here. So 2x squared is 2x to the fourth, which is what we want to cancel and get 0. Then we have minus 0x cubed, because 2 times 0 is 0, and 2x squared times 4 to get 8x squared. Remember that all of these are going to be subtracted, and so we're going to subtract this and get 0, subtract this and get negative 3x cubed, subtract this and get, what is 9 minus 8, 1. But of course, we have to bring down our next piece because we need a trinomial. And now we identify what can come from x squared so that we can end up multiplying and get negative 3x cubed. So we're missing a negative 3, and we're also missing a power of x. So we distribute that into each of these 3 pieces. And now we're going to get negative 3x cubed, yay, and 0x squared, and negative 12x, which we will subtract. So if I subtract, I get 0, which is what we want. And then here we're going to get 1x squared. And then over here, if we subtract, it's technically adding a negative there, or sorry, adding instead of subtracting. So we'll get negative 2x, and then we bring down our last piece of positive 7 and continue our long division without room. So yay for that. So I'm going to move it up here because I've clearly run out of room. And now we're going to ask ourselves what times x squared is going to get x squared. So not a lot can happen there except the number 1. And so if we multiply the number 1 into each of these, we get x squared, 0x, and 4 that we're going to subtract. So 0, of course, 2 minus 0 is, sorry, negative 2 minus 0 is negative 2, and 7 plus 4 is 11. And so that's our really icky remainder, which means that the solution is going to be this 2x squared minus 3x plus 1, but then plus the remainder of negative 2x plus 11 over the x squared plus 4 from the beginning. That is so not easier, but dividing was never said to be easier, so there you go. Alright, so in exercises 29 and 30, we need to use the remainder theorem to find the remainder when f of x is divided by x minus k. And we're going to check by using synthetic division. Super. So remember, this is given as the 0, so if we do synthetic division, we just put our negative 2 there and fill it in. But in order to get the remainder theorem, all they're saying is to take this and plug it in. Because if we plug it in for x, we're going to end up with the remainder from taking this synthetic division. So plugging in a negative 2 makes our algebra happen. Alright, so this piece is going to be negative 8 times 3, so negative 24. This section is going to be 4 times negative 2, so negative 8. This section is just negative 2 and then negative 5. Wow, that's a lot of negatives. And so then altogether, negative 24 minus 8 minus 2 minus 5 makes negative 39. And so that's our remainder. So if we double check with synthetic division, we're not missing any powers. So it's just a 3, negative 2, 1, and negative 5. Filling that out, bring down the 3. 3 times negative 2 is negative 6. Add those together, negative 8. Add the multiply those, 16. Add that together, 17. 17 times negative 2 is negative 34. Is that right? Yep. and that's really ugly, but either way, negative 39. Hey, which is what we got if we just did synthetic division anyway. Super! So remainder is negative 39. The next one, they want you to use the factor theorem to determine whether the first polynomial is a factor of the second polynomial. So the factor theorem is technically the remainder theorem. We just are looking for a remainder of 0. Because if the remainder equals 0, then whatever we've put in there is in fact a factor, because there's no remainder. So our 0, if our factor is x minus 2, is 2. And so we just need to plug in to x cubed minus 4x squared plus 8x minus 8. We just need to plug in for all of these x's a 2. So this first piece is 8, then we'll subtract 4 times 4, so 16, and then add 16, and then subtract 8. Hey, that's 0. So that means that x minus 2 is a factor of that cubic function. Super. Then we're going to use the rational zeros theorem to write a list of potential rational zeros and determine which of those are zeros. I'm going to need more space than this, but either way. The rational zeros theorem says that we need to take the last value, the constant, and the first value, the leading coefficient, and we need to find out all of the possible factors of the numerator and denominator, make all of the options for each of them, and then those are all the zeros. So, factors of negative 6 are going to be 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then for the second one here, the factors of 2, since it's prime, are just 1 and itself. So every single possibility of each of these as a fraction is going to be part of our probable zeros. So our list of zeros could be 1 over 1, which would get us a plus or a minus 1. If we keep with 1, we're going to also have plus or minus a half. Then the next piece, we're going to have plus or minus 2, and then 2 over 2 is 1, but we already have that, so I'm not going to write it again. Then we have 3 over 1, so we'll have plus or minus 3. And then 3 over 2, so plus or minus 3 halves. Oops, that's a fraction. And then plus or minus 6. And then 6 over 2 is 3, so it goes back to this one. So we kind of have repeating 1s and 3s, but it doesn't really change what we're doing. So now we just plug in each of these to see which ones make a 0. And the fastest way of doing that is actually to do it in the calculator. So if we put in this into y equals, and then make sure that in our table set we have independent table set, which is second and window. All you would do is plug in each of these into the table, and then you would find out which ones get you 0. So as I'm looking through, I put in each of these, and until we get to the number 2, that's when I actually get a 0 out. Listing again, negative 3 is nothing, 3 is 90, 3 halves is negative 9.7, negative 3 halves is 0, so negative 3 halves. And then since we have a power of 4, I'm guessing 6 might work? Nope. So that means that there must be 2 imaginary solutions. So these are the zeros that work. Alright. We will finish the rest of this assignment on the next video.